introduction. Good afternoon, everyone. Today I'm going to talk about our work on edible electronics. With edible electronics, I anticipate you, we mean electronics composed of materials that are approved as food from authorities like the European Authority or the American Food and Safety Authority. Why would you use food and how would you do that for electronics? Well, I will explain it in a little while. I think most of you are more familiar with ingestible electronics. Ingestible electronics was born in 1957, and then after 50, 70 years, now we have commercial devices. And the ingestible electronics is doing great and can do amazing things. However, at some point during the progress of ingestible electronics, a new field was derived. Just because many of the materials used in ingestible electronics are actually toxic, although encapsulated. Think about batteries. So ingestible devices, they use actual batteries inside. So there is a new derivation of this story where we try to use safe material inside ingestible systems. And there are many materials that are actually food, approved as food, which have very interesting electronic properties. So first of all, insulators. There are many insulators that you could use. For example, albumen or starch. Conductors, there are many conductors. Just think about the gold foils used in pastry. So gold is perfect, but also zinc, magnesium, calcium, and also what I'm going to talk about today, activated carbon. Activated carbon is an electronic conductor that we can use for edible electronics. And finally, there is also some semiconductors material. For example, beta-carotene is very well known to be semiconductive, although unstable, or indigo carmine, it's a pigment in food. And there is another pigment we just published. It's a pigment from toothpaste called phthalocyanine. It's a blue pigment, and it's semiconductive, so you can create, for example, transistors using that. So today I'm going to focus about activated carbon, and a blend of activated carbon and gelatin. And just to be provocative, we used Haribo's gummy bear to show that you can actually use normal gelatin. And the conductive ink is only made of gelatin, ethanol, water, and activated carbon. And it's spray-coated onto any substrate using, for example, a mask so that you can pattern it. And on the right, you can see an example of how the coating looks like. So that's the morphology. You can basically see that there is an agglomeration of activated carbon held together by gelatin. And if you start playing with the concentration of gelatin and activated carbon here, you will see that at the beginning, with low concentration of activated carbon, your material, it's not conductive at all. At least you might have some ionic conductivity, but it's not conductive. But as you increase the concentration of carbon with respect to gelatin, you start to have conduction. You have a percolation here. And with high concentration of carbon, you have a sheet resistance, which is not comparable to metals, of course, but still usable, for example, for resistive sensing. And of course, also, obviously, also the thickness goes up, but still in a range which is useful for example, for printed electronics. The impedance measurement just say the same thing. So low concentration of carbon is pretty much an open circuit, but then at some point you have percolation, and here, so for high concentration of carbon, the coating behaves like a normal resistor. And we have used this material for 4 different applications. We have used it as a gate material for a transistor. We have used for strain sensing, pressure sensing, and temperature sensing. And I will give you a very brief very brief summary of the results here. So for the transistors, we use an architecture that we already have in our lab using 3pH as a semiconducting material, and this is already published and working with PDOT. And what we have done here is we have changed PDOT with carbon, with this gelatin and carbon ink. And as you can see here, the characteristic is pretty much the same, meaning that the material is effective in gating a transistor. And the carbon material as a gate material, it's very useful because the surface area is very high. So you can use it for functionalization purposes, for example. Another application we have tried is strain sensing. So we have applied the coating onto an edible elastomer, also done with gelatin. So basically, we have a material that you can stretch. And then you will see that from here, from the SEM analysis, that as you strain the sample, you see microcracks appearing in the coating, which reduces, of course, the conductivity. And these self-cracks are also self-healed, meaning that you can reuse the sample for strain sensing. And here it's an analysis of the strain sensing results. First, we analyzed what is the dynamic range. So we want to focus on this part of the curve. So lower a strain from 0 to 8. As you can see here, this is the strain. So yeah, maximum 10, where we have a pretty much linear analysis, pretty much linear behavior. And then we analyzed it many times with different samples, achieving a gauge factor which is comparable also to the state of the art, and very linear curve. Also quite repeatable, as you can see here. And the coating, so we have seen electrical conductivity, we have seen stretchability, so we can use it for strain sensor. We have used it also for pressure sensing. For pressure sensing, we developed a small gelatin microstructure by molding, mainly. So you have basically two gold electrodes, and then you have a gelatin architecture using our coating here to create a conductive path. So it's pretty much a bistable pressure sensor. When you press this gelatin microstructure, you achieve contact, which is, of course, switching on the sensor. And then as you increase the pressure, the contact area will increase, and the conductivity will go higher. So as you can see here, for different height of the microstructure, at some point you have conduction, which means the coating is in touch with the gold electrodes, and then as you increase, you have a small, not such a high sensitivity here, but a small response to pressure. And as a final application that I would like to show you today is temperature sensing. So activated carbon, it's very well known to be affected by temperature, but also affected by humidity. And so as you can see in the middle here, in the central picture, just our coating is the black curve. So this is sensitive to humidity and also has some hysteresis here, which is not ideal, but also very sensitive to temperature. And carbon, differently from metals, has a negative temperature coefficient. So when you increase temperature, the resistance will go down. However, you can encapsulate this material. So as you can see here, we can encapsulate the material with edible material as well, which is mainly cellulose and wax, and edible gold foil to create contacts. So you can encapsulate it, and when you encapsulate it, your material becomes totally insensitive to humidity. I mean, virtually insensitive to humidity, because there is wax, and then you can use it again for temperature sensing. And so we have tried this to show that we have a small deviation from the exposed material, but we have a pretty good sensitivity for temperature sensing. So we can create a thermistor out of this. So to give you the idea, so to wrap up, I would say that we have, in a provocative way, we have used Haribo gummy bears instead of gelatin to show that actual food can be used to create devices. And we have used it with activated carbon to create a conductor that you can use, for example, for resistive sensing, which can be strain, temperature, pressure, but also shown it in a field effect transistor. But that is only one of the devices that we make. As I mentioned before, we have just published a paper where we use a pigment from toothpaste for edible transistors. One of the questions that always come up is how would you power it? Well, we have developed many versions now of an edible battery, so all edible materials creating a redox couple to generate a small voltage and a small amount of current. And also we are working on intra-body communication, which is trying to use your body as a communication channel to get out the data. So instead of radio frequency, you can actually use your body as a communication channel, mainly. It's there is an ionic conductor, an ionic conduction that we can take advantage of. Well, that was my last slide to show you that there is a whole idea behind to create a system, a full system that can be used instead of ingestible systems, but with an increased level of safety. So I would like to thank Mario Caironi, which is the principal investigator of my group. I would like to also thank all my group and the funding, my Marie Curie postdoctoral fellowship, for giving me the opportunity to be here and present my work. Thank you.